From the statistics that we saw all around the globe, we saw that developed countries, like in Europe, like in the US, Australia, around 17% of the energy of the country is pushing the water from the source to the end client. Now think out of those 17%, 30% are leaking.
Welcome to another episode of the Mapscaping podcast. My name is Daniel and this is a podcast for the geospatial community. Today I'm talking with Lauren Guy. He's the CTO and co-founder of a company called Astera. And in this conversation, we're going to cover a lot of ground. We're going to start off searching for water on Mars. Lauren's going to walk us through how we can use the same technology to look for leaky pipes here on Earth. And then we're going to talk about how we can build a business around it. Before we get started today, I want to say a big thank you to our sponsor, GeoAwesomeness. So I have done a bunch of work with GeoAwesomeness in the past, and every time I talk with Mutu and Alex, the two co-founders of GeoAwesomeness, I'm completely blown away by their enthusiasm for the industry. And now they're doing something which I think is pretty cool. They're creating an Earth observation hub. So basically this is going to be a section of their website totally devoted to Earth observation. So it's going to be curated articles, podcasts, webinars, and a lot of other information solely focused on Earth observation. And the idea is to make something for policymakers, business leaders, geospatial experts and enthusiasts to showcase how Earth observation is transforming the world. So this is done in collaboration with Up42, and you can check it out for yourself at geoawesomeness.com/EO-hub. But I'll put a link to that in the show notes as well. And if you just Google GeoAwesomeness EO Hub, you will find it as well. Hi, Lauren. Welcome to the podcast. You're the CTO and founder, I believe, of something called Astera. And the way I understand it is that you look for leaky pipes from space. But I think before we get into all of that great stuff, perhaps you could just take the time to introduce yourself to the audience and explain and maybe even confirm if that is what Astera does.
Hi, so thank you for having me. My name is Lauren Guy. I'm the CTO and founder of Astera. I'm a geophysicist by trade. And here at Astera, we are looking from space. We are looking for leakages under the ground without even setting a foot on the ground. Totally remote sensing at its purest.
And did you say that you're a geophysicist by trade?
Yeah, so my bachelor degree is in geology, and I continued in my master's to be a geophysicist.
How did you get involved in remote sensing Earth observation with that kind of background?
So when I thought about what should I study, as a kid I always loved maps. I actually went to sleep with an atlas, with a book of maps every night when I was a kid, and my mom always made fun of me. But maps were always around me. So when I thought what should I study, I actually didn't know if I should choose geography or geology. But geology was a little bit more interesting for me. So I studied geology. When I finished with that, I understood that it's actually more interesting for me to not just, tell about different rocks or soils or dinosaurs. Actually more interested in the processes that we have here in the atmosphere or on Earth or other planets as well. So I focused mostly on the geophysical aspect of geology.
And I believe that focus on the geophysical aspect of geology, that led to a project that you're involved in where you're looking for water on Mars. Is that correct?
Correct. So when I started my master's, one of the projects I was involved in is using radar sensors that's actually orbiting Mars. Yes, we have satellites orbiting other planets. And we use these sensors to look for any indicators of water on Mars. If there is water on Mars, it's under the ground, obviously. So we need a sensor that can penetrate the ground and give us a clear view what's beneath that. It's like an X-ray machine that you want to see beneath the body. So we use those radars to find indications of water under the ground. And luckily we found it. So yes, using the same project, we did find indications of actual water that are buried in Mars.
And I believe you said you're using radar satellites for this. Is this what we think of when we think of SAR satellites?
If you can take a broader look right now, so we all know the electromagnetic spectrum. I'm focusing on the microwave spectrum. Microwave can penetrate the ground. Microwave can penetrate a very thick atmosphere. That's why we also use microwave on Venus. We don't use microwave on Venus to find water, but the atmosphere of Venus is very, very thick, so we cannot see through it. That's why it looks very, very white if you look through a microscope. Yes, so microwave can penetrate almost anything. And in order to produce good microwave images, we use a method called synthetic aperture radar or SAR. So, yes, this is definitely what I'm speaking about.
Okay, so you successfully found, or you were part of a mission, a project that successfully found water on Mars. Right at the start of this conversation, we talked about how you were looking for leaky pipes on Earth. How does that translate? How does that technology translate from finding water on Mars to identifying leaky pipes in our infrastructure here on Earth? I'm assuming these are two very different problems to solve.
Yeah, so if I go back in time, when I finished my studies, I looked for something to do with my degree, and not many people are looking for geophysics people. So actually, my first job was a geologist survey here in Israel for one of the projects. It's a big highway project, and there I worked very close with a local utility. It was just next to Jerusalem, actually. And speaking with the engineers there, I found out that the water that we drink being transported for us, we all know that from reservoirs and people and locations that are quite far or from desalinating the water from the ocean. And actually 25, 30, 40% of those water are leaking into the ground. Think that they take water from the reservoirs, they transport it for hundreds of miles, and just a few meters before your house, it's leaking into the ground. So it's a huge, huge issue. And once I heard that, I had like it's like in the movies. I had this like light bulb above my head, thinking, oh, I can look for water under the ground. So that's everything clicked. Yeah, but of course, new issues came up. We on Mars we looked for any kind of water. Here we want to find very specific drinking water, which are treated. So yeah, that started the motion of how we can take this technology and apply it here on Earth.
That's kind of an amazing statistic that, I think you said 30 to 40% of the water that you transport around, drinking water that we're moving around the world through our infrastructure is lost through leaky pipes. Do you have any idea how much energy is lost while we're moving that water around as well?
So you're correct. Pushing water takes a lot of energy. From the statistics that we saw all around the globe, we saw that developed countries, like in Europe, like in the US, Australia, around 17%, 17% of the energy of the country is pushing the water from the source to the end client. Now think out of those 17%, 30% are leaking. You can imagine the huge amount of energy that is being lost. Right now, we're all conscious about global warming and we're all conscious about the carbon footprint. So it's just a big waste. So it's not just the magnitude of water being lost. And we all know that water is very important, but it's also the energy. It's a huge amount of energy.
Okay, so you've got this experience finding water on Mars. You see that we've got a problem. If we could identify a very certain kind of water, drinking water here on Earth, then we could use this to perhaps like help solve the problem of all this waste. So the waste of the water that we're moving around, of course, the waste of the energy that we're using to move the water around. So this is a significant problem. How do you go about finding drinking water? Like how do you go about creating a synthetic aperture radar signature for drinking water?
So we can start talking about what exactly synthetic aperture radars are measuring. And what we measure signals coming from the ground. And we're basically measuring the dielectric constant of different materials that the signal touches. How well this phenomenon or phenomena is conducting electricity. This is what we measure with synthetic aperture radars. So if we can define what's exactly the dielectric constant of drinking water opposed to any other kinds of water, you can isolate the signal of drinking water. We all know that drinking water are being treated, meaning they have a very distinct salinity level in the water, and salinity affects the conductivity. So if you can correlate those two, and we look only for the signal or the conductivity or the salinity of treated water in the ground, we can remove all other kind of water sources in the ground and only emphasize the treated water one. And we have the assumption that if we see treated water under the ground, it has to come from a pipe. There's no other source of treated water to be there. So that's the entire thought idea, yeah, and the founding stones of the solution.
Okay, so I immediately think of people that are watering their lawn, watering their garden. I think of a swimming pool. We use drinking water for a lot of different things, and we sometimes just put it directly into the ground. How do you avoid not finding a whole lot of false positives?
That's a great question because let's imagine a big city that we're working at, let's say Copenhagen or London, whatever city. You can imagine there are thousands of water sources in the ground, above the ground, where people watering their lawn, vegetation sometimes also looks like water. So, yes, there's a lot of different sources within the city. As I said, one of the methods is to only focus on the treated water ones, but there are other sources that might look like it. As you said, people watering the lawn. So it's all part of the calibration process and how you build your solution. Because we wanted to neglect those cases, we calibrated our algorithms to only show moisture in the ground that's accumulating for more than 48 hours. And that's why most people don't water the lawn for 48 hours. So that's why we don't see those very specific cases of a very, short period of moisture in the ground for whatever reason. And we only focus on the leaks that are actually there and staying there under the ground. So that's the way we do it.
So, if I understand this correctly, it looks like you're almost doing monitoring. So, you're looking at a specific geographic area over a longer period of time and seeing what the leaks that we find, the water under the ground that we find, also has to stay there for a certain length of time. Is that correct?
Correct. This is definitely a monitoring solution. We take an image of the city every defined time that we define with the utility. And we monitor the system and we alert if we find changes that might indicate a leakage.
So, I guess the question for me now is how far under the ground can you detect a leaky pipe? How far can the satellite penetrate the ground?
So, of course, a lot of people ask that how far can we penetrate? And they expect us to say hundreds of meters or tens of meters. But that's not really the case. Synthetic aperture radars or microwave, it can only penetrate a few meters. It depends on the soil type. It depends on what on top of the soil. It can be asphalt, it can be pavement, it can be nothing. But for all the measures that we've done within cities and urban environment, we saw that we can penetrate around up to 2 meters, which is okay because the pipes are around 1 meter deep. But if we go to more rural locations or if we go to outside of the city, the penetration sometimes can get to 5. If it's a very sandy soil, it can even get to 10 meters. It depends.
I'm not an expert in SAR by any stretch of the imagination, but I know that it's difficult to work with. I know because of the oblique looking angle of the sensor that georeferencing can be difficult, for example. I know from a previous conversation with you that telecommunications in urban environments that they create a lot of noise for the sensor. And of course, reflective surfaces also create a lot of noise. Could you walk us through some of these things and explain how you solve those problems?
So when a young researchers approach me and they say, I want to work with SAR, I tell him run away. it's a very it's a very chaotic and problematic method, especially if you come from the optical side of things. Synthetic aperture radars, especially in the bands and frequencies that we work at, they are the same frequencies as cell phones. They are the same frequencies as telecommunication devices. So when you take an image of a city, you don't see anything. You see like a white cloud of noise that masks everything beneath that. So that's a big, big issue that we needed to overcome in the beginning. We overcame it with different methods, mostly using different polarizations. Synthetic aperture radars can transmit and receive in different polarizations. Those different signals enable us to identify the source of the noise and remove it.
Could I just stop you there for a second? What do you mean by different polarizations? What is that?
So when we send a signal, we can send it in different methods. The electromagnetic spectrum, we can send it in a vertical method, and we can send it in horizontal method, 2 ways. And when the signal is touching different materials or different noises, the signal polarized. It goes from vertical to horizontal and the opposite. So if we detect those polarizations changes, and if we can detect the magnitude of those and measure them exactly, we can say what is the source that created this polarization and change of polarizations, and then remove it.
Okay, thank you for that. Now, I'm assuming that if we're looking for this kind of leaks under the ground, pipes that are leaking, the wastage of water and energy, a lot of this is going to happen in urban environments. You're talking about telecommunications creating a lot of noise in the signal. What about just the fact that the satellite is looking obliquely at a very complicated terrain? Like I'm assuming it can't see through buildings, for example. Do you need an extremely detailed surface elevation model or surface terrain model to figure out what you can actually see from the satellite and georeference against that to find out where these pixels are landing on the surface?
So SAR satellites are not looking in nadir, as you said. They're looking from the side, and those side images really deviates and doesn't really make a lot of sense if you not georeference them to the right location. Also, the georeferencing error is not constant. You can have an error here for 20 meters, and if you go one block away, it can be 100 meters, and sometimes it can get to kilometers. And as you said, it's basically related to the topography. It's basically related to different radar errors that might be introduced into the image, like foreshadowing and things like that. So georeferencing is very important. Most of the satellites that gives you the georeference, the image, the images are not georeferenced. They don't do that service. And if they do that, by the way, it's not very accurate for our means because we want to find a very precise location. We don't want to find the leakages in a place that we tell the client that and is looking for that in another place. So the exact location is very important for us. So in the beginning, in order to make a good georeferencing method, we actually had a team of people looking on the radar image, looking on an optical image, and connecting each pixel of the radar image to the actual pixel on the optical image so we can see the right location on the ground.
Wow.
And you can imagine with an image of 5 million pixels, it takes time. Yeah, it was a big team. Usually one image took a week to georeference, and it was a big issue. And of course, you cannot scale up if you are doing this method. So we started developing a way to auto georeference synthetic aperture radar images. You are correct that we are using a DEM doing that. And we also are doing some calculation based on the information we get from the satellite. And yes, we successfully created a model that can auto georeference L-band synthetic aperture radar images in a few seconds. And it's not very, very, very accurate to the magnitude of centimeters, but it can take a deviation of hundreds of meters and take it to a resolution of 5-10 meters, which is more than okay for us.
Okay, so it sounds like you've had to solve a lot of problems along the way, and you've identified the signature of water, and you're finding water, you're finding these leaks. How do you ground truth something like that? So I'm assuming at the end of your pipeline, the result of this process is a map or some locations where you say, we think there's a leak happening here. How do you go out and ground truth that, prove that your process is giving the correct information?
I think that a lot of remote sensing solutions don't really close the loop. If we think about the most obvious one, let's say NDVI. So if a company gives insights of NDVI, no one really goes to the location and check if the exact value that you gave is the actual value that correlates to what you saw in the field. So no one really validates the insights that remote sensing gives in most cases. But because we had to find very specific issues and to measure very specific signals, that wasn't the case for us. So from the beginning, when we started creating the solution, we actually simulated thousands of leakages under the ground in multiple places around the world because we wanted to have one global solution, one global product that can work everywhere. So we had to ground truth it in many, many locations. So that's how the algorithm evolved. And once it went to a solution, to a product that we are selling, we give the insights on top of a web map. We give the insight on top of a smartphone application. So when the end client or the utility goes to the field and verify the location that we told them about, they're actually reporting back on the application if it's a leak or not. And if it's a leak, what are the different parameters that related to that leak? If it's not a leak, what are the different parameters on this area? And that's refeeding our algorithm and making it better and better in machine learning processes. So always validating and closing the loop is one of the most important things for us.
So based on these insights that you're creating, are people going out and digging holes and looking for leaks, or are they doing something else to determine if it's correct, if there is actually a leak there?
So if we are describing for a second how this leak detection world conducted before we came, it was very, very simple. A team that belongs to the utility walked around the city, street by street, meter by meter, and look for indications of leakages. They didn't need to dig everywhere because if there's a leak, there's usually an acoustic sound that being transformed on the pipe. So they listen to the pipes through hydrants or valves or other metallic objects that are above the ground. And they looked for a leak, walking everywhere. And they maybe found one leak a day, and they were big heroes doing that. When we came to this game, we told them, you can do the same thing you are doing. You can still walk the streets. You can still use the same verification methods that you are using now, but instead of walking hundreds of meters or kilometers or days looking for an indication of a leak, we give them a very precise locations, a buffer of a few tens of meters where we suspect is the leak. They go to that location only. They verify it with their own known methods. They verified it with their own acoustic devices. They don't need to dig. And only if they verify by acoustic devices that the location I gave them actually sounds like a leak, then they dig and they fix it. So there's actually two verification processes. One is mine, the insights that we give from the satellite. And the second verification method is the one that they're used to do. They're using their verification method to double check if our indications are correct. Because as any other signal processing algorithm, we are not 100% correct. In the beginning, we were only 20% correct, which sounds awful, but it was commercial back then, because back then, with even 20% success rate, they can find 2 leaks a day, and it was twice better than what they have. And today, once we approach the 86, 90% success rate, of course, the assurance in the technology became better, and they can find much more leaks every day.
So when you first developed the system and you had a product that worked, you'd done your ground truthing and you went out to the market and said, hey, look, I have a satellite in space. I'm going to shine some microwave radiation down on Earth. I'm going to look through your streets and find all the leaks in your infrastructure. It sounds like fantastic. It sounds magical. What did people say when you said that to them? What was their response?
No one wanted to buy this solution. So yes, I thought that everyone is going to get into line and buy it, and I'm going to be a millionaire within days. No, that wasn't the case. Let's all remember that water utilities are very old-fashioned. They are used to the methods that they are using for, I don't want to say hundreds of years, but for a very long time, since the 1900s. So coming to them and say, hey, listen, I can see everything from space. They were a little bit skeptic about that. And actually, no one believes us in the beginning. It was very hard to convince them that we can see things from space. I think they saw us like a group of charlatans or I don't know what. So yes, we had to prove them. Actually, in the beginning, in order to show them that we actually mean what we say, we sent our salespeople to the first meeting with different utilities with the leaks of the utility already examined. So because we couldn't take an image every location on Earth before the meeting, we took an image of the utility, we scanned it, we created the insights, and the sales guy got to the utility already with the map of their entire system and the leakages. And when the CEO or the decision maker is looking on a map that shows him his problems without even for him to give a consent. By the way, they were shocked that we can take an image wherever we want without their permission. So once they saw it, they couldn't ignore it anymore. I'll have to say we were a bit naughty in the beginning and we were a little bit aggressive, but that was the only way to show them that we know what we're speaking about and we can show you your problems, some of the problems you know about already, so it can create the assurance that you want in the technology. But yeah, we have it's proof science and it can really help you. And that really helps moving things forward. It doesn't mean that it's very easy to sell it even now, because once we overcame the question, if that works, we came to the questions, what is the ROI of that solution? How can it give me benefits opposed to other solutions that I might have? So that's a good thing. You want to deviate the discussion from the technology to the business discussion. And we're also very good on that side of things. But yeah, it was very hard to sell in the beginning.
Can we stay with the idea of the business discussion just for a second? Because I think this could go either way. Like you could show up with your pocket full of magic and your image of all these potential leakages in their infrastructure and say, look, I've solved all your problems. That's one way they might understand it. Another way they might understand it is like, look, you're not doing a good enough job. Is everybody eager to see this kind of information? Are they eager to understand where they have leakages in the system?
No, there are many types of utilities around the world. Most of them are very passive, meaning they are not really actively looking for the leakages. They're just waiting for some citizen to call them and say, oh, I have something in front of my house. Please come and fix that. So if you come to those utilities, which basically they do nothing, and you tell them, oh, please spend a few tens or hundreds of thousands of dollars on an image that can show you everything, although if you will look on that from a pure financial point of view of saving water, which is money, it's very hard for them to justify an expense that they didn't do in the past. It's very hard, mentally to do that. Although they can see the ROI, they're not used to spend money on that subject. So that's one type of a utility, and a lot of ROI. We have to convince them that the ROI is solid and they should buy it, but it's very hard. The best kind of clients are clients that are already solving this issue, and they can solve it in a different ways. The first one is, as I said, is just walking randomly. They have a team of people. They're just walking randomly in the streets and looking for the leakage. It's very easy for us to show them the ROI of that team opposed to our solution, and to show them that, it gives them a lot of benefit. We actually measure that in a term called price of leak. How much money it costs them to find the leak opposed to how much money it costs with us to find the leak. And it's much, much, much lower than us. So those guys have a budget for that, for looking for leakages, and they can just take that budget and bring it to our side. So it's much easier to work with those guys. And then there's the third kind of utilities, and those are the most advanced utilities that they not only have people working, they also have very expensive equipment Internet of Things, that they communicate with each other, and they communicate back to the utility about location where it's suspect there are leakages, and they need to go and solve those issues. And of course, those devices cost a lot of money, a lot of capex. It's a big, big investment. So we are more on the OPEX side of things, on the operation expenses. So you cannot compare that to that, but we are actually complementing this technology. We say, okay, yes, you have a very expensive sensor. That's cool. And you can keep those. But because usually even very big cities cannot cover their entire city with those equipment because they are very, very expensive, they are using our technology in a macro level view, not just a one leakage view, of what are the most problematic areas within the city. And then they know where to take their equipment and shift it to the new location. So it's called lift and shift. They lift the equipment and they shift it to the location where we think is the most problematic one. And that gives them a great solution. If you solve an issue with two different kind of technologies, that's the best. But that's very pricey for most of the utilities.
This is really interesting. So a lot of the times when I hear people building businesses around Earth observation techniques, like what you're doing, I feel like this is the only solution. Earth observation is the only solution, and they completely negate any other ideas that are out there in the market. You seem to be approaching this almost like this is a symbiotic relationship. I can do this, I can speed up the process, and you can continue doing what you're doing. And what you're doing provides feedback to me so I can get better at what I'm doing. Am I understanding this correctly? Is that your approach to addressing this market?
Definitely. In order to sell to those guys, we had to speak their language. We actually went to the field in many, many countries with the teams, looking for leakages, looking what they exactly do, learn their methods, everything. My son actually called me a plumber from space because I did it so much. But yeah, that was the only way to gain their trust in our technology, because we went there in the ditches with them, with the yellow vest and hard hats. Yeah, so I think selling to a very old-fashioned customer, it doesn't have to be utility. Any old-fashioned customers, even in the defense market, you have to show them that you speak their language. You have to show them that you can work with other solutions, because you don't come to avoid. They did something before you came. So you need to work with that. You cannot say just throw everything you've done and use only us, because it's not going to work. Also, people don't like to confess about their mistakes. A utility is not going to say, oh, I spent $50 million on equipment. I'm going to throw that away to use your equipment. No one will ever say that. So you have to work with different kind of utilities and a lot of different methods, and you have to work with that.
I really appreciate you sort of sharing your insights around this. I think it's really, really important for people to understand this. Those of us who are thinking about getting into the space, perhaps creating a business in the same way that you have done, working with people and ideas and solutions that are already there. I think that there's some really brilliant insights there. Thank you very much for that. I'd like to kind of move on now because you've walked us through this process. We started out looking for water on Mars. Now we're looking for leaky pipes on Earth and the infrastructure that we use to move water around. You talked about some of the challenges that you've faced along the way and the solutions to those. What else can we use this for? So when I think about this, I think, I wonder if we can use this to find contaminated water, for example. Yeah, how can you build on top of what you've already got?
So, although from the beginning we were quote unquote a water company, I always thought that water is a case study to show that we can achieve something using this technology, but the sky is the limit. You can take this technology and apply to different verticals. So, from there, the most obvious thing for us was to stay in the infrastructure market and look for issues around important infrastructure like highways, like railways, and find indicators that might affect those. Not a lot of people knows that, but most of the issues in infrastructure are because high soil moisture, water that is not being drained correctly, water that is being accumulating next to bridges, under highways, under railways. And if you can pinpoint to those locations, you can help very big utilities. Think about a very big railway company in a country or Department of Transportation of another country. If you can pinpoint those clients to the right locations that might fail very, very soon. And let's not forget, we are looking under the ground. So the issues that we see are not apparent for them yet. So that was a very obvious move for us to go from very specific kind of water to soil moisture in general. So that was our second product. And yes, as you said, we are slowly developing other solutions like contaminated soils, some things in the defense market, some things in mineral explorations. You can really apply these technologies to many, many other things and use the power. You can penetrate the ground, you can see in day and night, you can see in any kind of weather. As I said, you can measure the signals, the electric constant signals of different materials, so you can identify those very precisely. There are many usages for this technology.
Is there any part of you that worries that somebody else is going to see the business that you're building and the problems that you're solving and go, great, I am going to copy paste that. I am going to start my own company. I'm going to get access to the same satellite platform that perhaps you're using and do the same thing. Does that worry you at all?
If you're looking for studies around synthetic aperture radars, you will see that most of them are referring to soil moisture. Most of them are referring to water because water has a very high dielectric constant. It's very apparent with SAR, so it's known. You can find water in radar. Most of our IP, and actually I always say that 90% of our IP is actually not finding the water. It's cleaning the noise. It's signal processing, about manipulating the signals so we will be able to see better. And we gained this knowledge along the time. As I said, we found 60,000 leakages all around the world. So our database knows how to work in different scenarios all around the world. So there's a lot of value in that. But you know what? I really love when there's competition, because if you go into a void, like a blue ocean, when you are the only solution, it's very hard to justify the market. It's very hard to say, okay, there's a market here, but no one else is selling to that market. So that market might not be valid because why there are no other solution. So once we see more competitors, and there are competitors, not exactly in synthetic aperture radars and not exactly with the bands that we're using, but there are lately some remote sensing solutions for soil moisture and for leak detection. And we actually love this competition because it really, it shows that our technology is superior. So you can compare it to other stuff and it makes you better, because if the client cannot compare you to similar stuff, he might think that you are not the best. So that's great. And the second thing is that it creates a lot of discussion. When we started 8 years ago, no one spoke about looking for leakages via remote sensing methods. No one. So when we came to that field, as I said, there was a lot of skepticism in the beginning. It was very hard. Now, when it's coming more quote unquote obvious and more common, and this discussion is being made around that, it's actually making our life easier because, okay, now it's a legit solution. There are companies offering those solutions. So competition is always good. I always say that.
Thank you very much for that. So you've been going now for 8 years. If you could go back in time and talk to yourself 8 years ago, what would you tell yourself? What advice would you give yourself?
It's funny, but I don't think that the water leakages business was the best business to start with. As I said, it's a very old-fashioned market, and it was very hard to prove the business case in the beginning. So, for a new startup which want to go fast, it usually wants to work in verticals where it's more private and less governmental. You want to work in a vertical which is not such a blue ocean. As I said, you want some competition because it can help you in the beginning. So I might have choose a different vertical in the beginning to showcase the technology. But, in the end of the day, things came up okay. But I think other verticals might kickstart things a little, maybe even faster in the past.
So it sounds like it took a while for the idea to catch on. What was it that kept you going through those years, I guess, before the idea caught on, before people could really see the value in this?
So the company was founded in 2013. I actually was alone until 2015, 2016. It was a one-person show because it was very hard to show that this technology can give benefits in the commercial purposes to a city. Because, as I said, it's signal processing, it's not accurate. We were around 25% success rate in the beginning. So it was very hard to prove the business case around it. Only in 2016, when the algorithm became better and additional people joined the company, people that knows how to sell. I don't know how to sell. So when actual salespeople joined the company, and we got a CEO with a lot of experience that knows how to sell and how to manage those operations. That was the big push in the back. So yeah.
Lauren, I really want to thank you for slowly but surely sort of walking us through what it is that you do, how you do it, how you solve these challenges that you meet along the way, and also diving into the business side of it. This is something we don't talk about very often on the podcast, but I really appreciate your insights and your patience. So thank you very much for that. If there's somebody listening to this and they want to get a hold of you, reach out to you, connect with you in some way, shape, or form, where is it that they can go to do that?
So the best thing is, of course, looking for me on LinkedIn. My name is Loren Guy. I'm one of the only people with that name, so feel free to find me. Also, feel free to go to our website, which is Asterra, ASTERRA.io. You can contact us directly from there. And yeah, I'm very approachable.
Yeah, I know that from personal experience. I really appreciate your time, Lauren. Thank you very much.
My pleasure. Thank you for having me.
Thanks again to Geo Awesomeness for helping make this podcast episode possible. And if you're into Earth observation, check out the Earth Observation Hub, EO Hub at Geo Awesomeness. This is done in collaboration with Up42, and I think it's going to be an absolutely fantastic resource for policymakers, business leaders, and just people that are enthusiastic about the possibilities of Earth observation. Search for Geo Awesomeness, EO Hub, or I will put a link to this in the show notes as well to make it easier for you to find. So I really hope you enjoyed that episode with Loren Guy from Asterra. When the mics were turned off, Lauren mentioned a few of the ideas that they're working on there, and it sounds really interesting. This is a company that I think would be worth keeping an eye on. If you enjoyed this episode, I can highly recommend an episode called An Introduction to Synthetic Aperture Radar. There's also an interesting episode around monitoring flooding from space, again using synthetic aperture radar. And if you're looking for a podcast episode around a really sort of practical application of Earth observation, check out an episode called Counting Animals Using Satellite Imagery. I think that you'll find that interesting. Okay, that's it for me. That's it for this episode of the Mapscaping Podcast. I'll be back again next week. I hope that you'll join me then. We'll talk soon. Bye.